Sì, sì, pronto. Okay. Right, so we were left in the middle of the computation yesterday. So the first part of the lectures today hopefully quickly finish the computation of the two-point function using the bulk-to-boundary propagator, which I introduced yesterday. I don't want really to spend too much time on that. And next thing I want to discuss is the idea of holographic normalization. So I will introduce the idea, and then I will apply that in our favorite example of the scalar field in ADS, which is the simplest case, perhaps. And then I would like to start, at least, if not finish today, the application of holographic normalization to the computation of the Weyl anomaly, which is then known holographic Weyl anomaly. So that's the anomaly in the conformal symmetry. So that's never the best way to start a lecture, which is to just finish a computation that was started the previous time, but that's what happened today, unfortunately. So let's write at least a step that was written yesterday. We had the field in the bulk, which was written in terms of, that's the important one. The field in the bulk was written in terms of the bulk-to-boundary propagator, in terms of the source at the boundary. With this picture of a propagating phi naught from a point x prime to a point in the bulk phi of x. And the other ingredient that we computed was the bulk-to-boundary propagator itself, this Green's function, which was some constant, and then z to the delta, where delta is by now related to the mass by the standard formula. X minus x prime square. So, well, maybe here I should put really the norm in Euclidean for space. Everything to the delta. And the on-shell action computation reduced, as in the momentum space computation, to a boundary integral surface term to evaluate at some cutoff of d for x with some constant 1 over z cubed, and then this form flux factor kind of. Everything is a function of x and z. We don't transform in momentum space. So this was where we got yesterday. So this should be already in your notes, I suppose. And we notice from the behavior of the bulk-to-boundary propagator that indeed, as z goes to 0, phi goes to z to the 4 minus delta times phi naught of x. So this reproduces from this point of view exactly the behavior of the Bessel function that were reproduced yesterday when you do the transformation momentum space. Right, so at this level it's just a question of plugging exactly this expression here and this expression here into this integral, and you get some triple integrals to do. So I will not take care of constant factors for this computation. So from now on, I will write this. So we get an integral in d for x, 1 over z cube. So now we are really, z is going to 0, so epsilon is really going to the boundary. So we can substitute for phi, we can substitute its boundary value. But we have to be a little bit careful when you take the derivative. Sorry. Early morning. When you take the derivative of the scalar field phi, you get some extra contribution. So here we get this z to the 4 minus delta, phi naught of x, and from the derivative part, you get this z to the delta minus 1, d for x prime, phi naught of x prime, x minus x prime to the 2 delta. Okay. So remember that here we are really going, I write here z, I could have written epsilon, it's equivalent. So for example, here in the propagator, after we take in the derivative, we can neglect the z in the denominator. That's why it disappears from this. Okay, so the computation is basically finished. You see it's actually, in a way, easier, much easier than in the other method yesterday. So this becomes a double integral. It's a non-local expression. And from here, it is absolutely already clear that the two-point function will be given by the same result that we got yesterday, right? So we have to take two variational derivatives with respect to the source phi naught, and then either you put it to 0 or not. It doesn't matter because that's just quadratic. But in any case, that's the result of the two-point function. So why did I say Witten's diagram? The reason is that this kind of a local structure globally has been depicted by Witten in terms of some cartoons, these diagrams, in which ADS is our beloved disk, and the bulk is inside the disk, and the boundary is the boundary of the disk. So this is ADS. And so a point in the boundary, like here, is then connected to another point in the boundary, in this case x and x prime, right, by this propagator, which is called k. So that's the simplest example of a Witten's diagram, in which you have only the propagator. But then this can be generalized by thinking that there are interactions. So, for example, so that's the two-point function. If we want the three-point function, then we will have a three sources at different point x, x prime, and x double prime on the boundary. Right? And then they will have to be connected with some vertex. But of course, as in Feynman diagrams in quantum field theory, which kind of vertex we have depends on the Lagrangian. So if we really want, for example, to have a cubic vertex, then we have to consider a term in the on-shell action, well, gravity action, that contains a cubic term. Yeah.
Try to see why both x and x prime on the boundary.
Well, the boundary is so the boundary. Let me finish this picture because it's left unfinished. Okay, so the boundary here is at z equal to epsilon going to 0. So that's why we are on the boundary.
Because our probability is from boundary to bulk.
Exactly, and this is the bulk. So these are three propagators that interact at a vertex inside the bulk. Well, okay, good point. I think it's called still K. It's a special case. Yes. Yeah. I just wanted to mention that there is a different guy, different propagator, which is the bulk-to-bulk propagator that appears in computation. So, right? So is this clear what is going on, more or less? I'm not going to do these computations, but right? So you need the quadratic term, which is like the kinetic term for the scalar field, to compute two-point function. But if you want to have non-zero three-point functions, you need some cubic interaction. So it depends really on which potential you have in your bulk Lagrangian. So another type of diagram could involve four-point functions. And then here is where you need a new kind of object, new kind of propagator. Let's not put labels anymore. So you need 4 of these bulk-to-boundary propagators, which in the special case becomes boundary-to-boundary propagator, and one new propagator, a bulk-to-bulk propagator, that takes from a point in the bulk to another point in the bulk. And how is this set up? So let me explain a little bit more. So the way to set this up is exactly as in when you do Feynman's diagram. Then you're doing perturbation theory in quantum field theory. So you need some small coupling, and you do your perturbation theory. And here, similarly, one is doing some kind of perturbation theory. But what is the perturbation theory? So we have to we assume that the full bulk action is given by the kinetic term, so the quadratic term, plus the interactions. And for example, here I wrote a cubic interaction. So here, this lambda is not the 't Hooft coupling. Just some constant that appears in your effective theory. Then the equation of motion is modified. And becomes of this type. And then it quickly becomes untractable. You can't anymore really solve exactly these kind of equations unless the potential here is something very special. I presume in some cases one can find exact solutions. But typically, if you have a power law, for example, you can't find a solution. So you do a perturbation theory, and the perturbation theory is done into this auxiliary coupling constant, which is a constant that appears naturally in the supergravity, some combination of the parameters. So then we take our full field phi, and we expand it in various terms. I use this notation with the square to distinguish from the phi naught that appears there, and the phi 1, etc., that appear in that kind of expansion. So this is a different expansion. Dot, dot, dots, where phi, the first order, or rather the zeroth order, is exactly what I was called phi before. So this is a function of x and z. It's an integral in d for x prime k of z x prime phi is 0 of x prime. So that was, at first order, it is exactly the same as before of the free case. And then you have to solve this in a recursive way, right? So you plug this phi into that, and you will get various terms, and it's kind of recursive expansion. So at the first order, you find that this is given in terms of the zeroth order term, and it has the coupling constant. So although I didn't put the coupling constant there explicitly, it starts to appear here. So you get linear, and then at second order you get quadratic, and so on. And then you have now a double integral d for prime dz prime is g, z prime, x prime, and then in this case you take phi naught, which is a field in the bulk, everything square, where this is the bulk-to-bulk propagator, which is defined by taking the following Green's function: g square root of g, so has delta z minus z prime, and delta 4. So it's a delta in five dimensions. Now, for k, I gave an explicit expression. For g here, there is also an explicit expression that you can find. It's given in terms of some hyperbolic, hypergeometric functions, and you can find in the literature. I don't want to go more into details here. So, in principle, by this kind of perturbation theory, you can compute higher point functions. You can also have cases where you will start having loops, depending on the type of vertices that you have. And then, again, these are easy words to say, but I just wanted to give the idea. In principle, you can consider correlation function of operators which are not scalars. So, for example, correlation function of conserved currents and whatnot. So, okay, I want to stop with this now and then move on to the holographic normalization discussion. One over n corrections. I would say that these diagrams are not directly related to the diagrams in field theory. Maybe I'm mistaken, but I don't see the immediate relation. I should think about it more. If anyone knows the answer, please. I mean, the reason why I'm saying that is that these are all computations done in supergravity, just in the classical supergravity. So I think these are all just in the Lagrangian limit. You want to make? Okay. So holographic normalization. So when we looked at the computation of the two-point function, which we did in Fourier space, we saw that when when z goes to 0, there are divergences. And I mentioned that I would, for the moment, just neglect those and come back to that later. So this is really analogous to what happens in field theory. Somehow, guided from field theory, we know that whenever there is a divergence, then we should not panic and try to regulate the calculation, which is something which we have already done. That's the regulator, right? So extract in a meaningful way the physical result, and then take the cutoff or the regulator away at the end. But that's the critical point. The critical issue is how do we do this regularization, and what does it mean, the result? Because essentially infinite plus finite, right? That's the danger, is still infinite. So when you subtract away some infinite part from a finite result, there is a huge ambiguity in how you do that. You're saying I'm removing infinity from a finite result. You could get anything that you like. So the way in which this is fixed in field theory, in quantum field theory, is that we want to, when you do the regularization and the normalization, we want to respect some symmetries. So that's what saves the day somehow in field theory. So we have to declare what are symmetries that we want to preserve. For example, very important symmetry is the gauge symmetry. And then that fixes for us, or at least puts severe constraints on what kind of regularization we can do and how we subtract the infinities. So similarly here, we want to respect some symmetries. And the symmetry that we want to respect in this procedure will turn out to be, well, the symmetry of the conformal problem, so the symmetry of ADS. Right? So if we do our systematic procedure of regularization and normalization by respecting the symmetry of ADS, then, well, that's a prescription that in the end will give some meaningful result. Okay, so this is how we will address the problem. But to show you how this divergence is really intrinsic to ADS, it's not something special that has to do with a two-point function that computed here for scalars. It's a general feature of ADS. It's just enough to look at the Einstein-Hilbert action, which we actually will readdress towards the end of the lecture or at the beginning tomorrow. So the Einstein-Hilbert action with the cosmological constant was just proportional to some, in general, d dimension. In fact, I don't have to be in 5 dimensions necessarily. This goes back to the first lecture. That's the action, okay? And then ADS, for ADS, if you take the Ricci scalar of that, which is this, that you can compute from the Einstein equation, and you plug it in, you find that essentially the action on shell reduces to just the volume form of ADS, integrating ADS. And that's where the problem lies. So on shell means evaluated on the solution of the equation of motion, taking this language from field theory. This is given by some constant, which I'm not going to write, and then an integral in d minus 1, which we could think of regulating in some way, or putting that on the sphere, for example, depending on which coordinates we are choosing. For example, if you are in global coordinates, this would be some compact part. But there is always, and inevitably, some non-compact integral to do, which in these z coordinates, for example, is something like that. So here, the divergence appears near to z equal to 0, where you can see that this integral diverges. So this is really a general feature. It is not to do only with scalars. It has to do really with the fact that ADS has an infinite volume and is a non-compact space. So in general, we can consider a system where the equations of motion that I'm writing down involve both the equation of motion for the metric and for whatever matter field is present. The simplest case would be, for example, a scalar and the metric coupled together. So there would be an equation for the Einstein equation for the metric, which involves the energy momentum tensor of the scalar, coupled to the Klein-Gordon equation for the scalar. So in general, you have to expand all the fields, including the metric. But then for simplicity, one can sometimes reduce focus on one case or the other. For example, here we consider the scalar in a fixed background. But if you have the coupled system, then it is a bit hopeless or naive to think that the metric will always be exactly ADS. So the metric itself, in general, does not need to be ADS. But we can take G mu nu, as I already mentioned, I think at some point, to be asymptotically ADS. Or even more generally, this locally, right? But without going into the technicalities, I will soon enough introduce a particular coordinate system where we will take that as a synonymous of asymptotically locally ADS. That's the coordinate system of Pfefferman and Graham. So what I mean here is that in order to do holography and in order to set up holographic normalization, that's the correct setup to consider. It's not just pure ADS, but a space which in principle it is asymptotically locally ADS. So it approaches ADS near the boundary, but it departs from it in some perturbative expansion near to the boundary. So in practice, this means that we can choose a metric which looks like that. So once we choose the radial coordinate, and for example, we choose this to be our z, then the transverse part, the metric transverse to the direction z is, let me use indices I and j. And this metric here, well, if we were just in ADS, this would be just the flat metric on Minkowski space. But for a space which is asymptotically locally ADS, this takes, in general, an expansion. So it depends on x and z. And it has an expansion which starts with the term which is just depending on x. And then other terms which have powers of z, exactly as we did for the scalar. And then there is a term that depends on the dimension. Here I'm considering ADS d plus 1. Then there is some g d ij of x, h d j of x, log z square, plus an expansion continuous. So this term, which is in these coordinates, is for obvious reason referred as logarithmic term, appears only if we are in dimension d, which is even. So in particular for ADS 5, only if d is even. So I will often put this kind of logarithmic term because our main interest is ADS 5. But we could equally be interested in ADS 4, and then this logarithmic term and similar logarithmic terms, which I'm going to discuss over and over in the next part of the lecture, would not appear, right? So our focus will be in d equal 4, although we can most of the time do the computation by keeping general d, right? So I can illustrate the structure keeping general d. In fact, if you compare this expansion here with the expansion of the scalar that we wrote, you can see that that corresponds, at least formally, to that kind of expansion by taking, so, let me write here. To the expansion of the scalar with delta equal to d. Right? So remember the expansion of the scalar started with the z to the 4 minus delta, which in general would be z to the d minus delta. So in fact, in this case, it starts with z to the 0. Right? So that's what I mean here. And similarly, this structure is respected. We will see that in more detail later. So this is also compatible this is a bit vague, of course, because the metric is not a scalar, but I'm just pretending it behaves like a scalar. So it's compatible with the fact that the metric would not, I mean, at linearized level, would not have a mass, the graviton, right? So it's a massless field. And it is also compatible with the fact that the metric, as I mentioned, coupled to the energy momentum tensor, which is an operator of dimension d in general. So either if you take a scalar, or if you take the metric itself, or if you take a gauge field or a fermion, any field that couples together in a system which has a solution which is asymptotically anti-de Sitter, you can do all these kind of expansions. For the metric, this is known as Pfefferman-Graham. Which are the mathematicians that worked out this theorem that you can always write asymptotically locally ADS into this kind of coordinate system. For the other fields, there is no analogous theorem, but there are explicit computations that show that, in fact, you can, well, I should not say you can always, but let's say in all the cases that normally people address, one can put these fields in such expansions. Although when I say always, one should always be careful and beware that there could be some caveat that you should add some extra term. So it is always something that it should be checked in your specific system that you are given. But of course, in the simple examples that we consider, which are the canonical examples in the literature, these expansions are possible and they can be done. Right? So what do I mean that the expansions are possible? It means that if you postulate these kind of ansatz for the expansions and you plug into the equation of motion, then you can solve them order by order. This is a bit like we did yesterday for the scalar, and we saw that, for example, if you postulated some power expansion in Z, you would find a solution which in fact in that case could be exactly resummed to this Bessel function. Yes?
So I just don't understand some of the dots in the expansion. So the first dot, what, you maybe write the second term?
Yes, the second term. What is the second term? Is it some power?
Does it have one power to Z or any
I think it's a square. In principle, it has all powers. But now, I think in some cases, in simple cases, the odd powers vanish. But okay, I'm not exactly sure what is the criterion for the vanishing. So in principle, it has all powers.
Is there a dot within the parentheses of the Z to the D term as well? Or is that?
There is no dots in the parentheses.
That parentheses exact, and then the dots afterwards just continue.
Yes. And in fact, thanks for asking this question, because I should say something important, something which I mentioned for the scalar, which is also true for the metric, and it's the following. That once you write this expansion, then this is a boundary condition, so it's free. These other terms are all fixed in terms of this. So this is actually an important remark that I forgot to make. I would have made later, but let's make it now, it's better. This one, instead, it's free. So this is the caveat that I mentioned yesterday, that there was almost everything is determined apart from something, and the something is this term. And the dots that appear here, they start becoming quite complicated because they have a combination of powers and logs in various increasingly messy combinations, but they're all determined by whatever is written here. So you don't gain new information. So once I tell you that the expansion has solution at any arbitrary order, then if you fix this and that, then you will find the solution. I will say a bit more when we talk about the Weyl anomaly. I will give some expression of some of these terms in terms of this to illustrate exactly how this works. But just in general, as I said, whenever we have such expansions, then at the end we have to plug them back into the action, exactly as we did for the pure scalar, right? Because then we want to determine the action as a function of phi 0, as a function of g0, as a function of whatever boundary term we have. And then if we do that, because of these expansions, all the terms will rearrange in the following expansion in the action. So I call this S regulated because it is evaluated at some Z equal to epsilon, and it is given by an integral in the dimension, right? Because we are now at some. It is always like a boundary term, like for the scalar, right? So there is no integral in Z anymore to do, and you are to be at some particular value of Z, and then you have a square root of g naught. And then the expansion takes the following form. You have epsilon. So the most divergent term is minus 2 delta plus d. Then you have some term a0. Then here the next term is epsilon minus 2 delta plus d plus 2, a2, plus some dots. Then if you are in even dimension d, you have the logarithmic term. And then you have the finite part. Finite meaning when epsilon goes to 0, they go to zero, or finite. Sorry, finite plus something that goes to zero. So this is always the case for whatever field you have. Here, I've considered the expansion of one particular field only. So this could be, for example, the scalar, which had dimension d before, but it is a generic feature of any expansion of this kind. So this is the S on shell, again. So in order to regulate that, well, this is already regulated, so in order to make this finite, as we did for the scalar, we have to kind of throw away the infinite part. And to do that formally, but something which will become useful later, we define a counter term. So a counter term is something that you add to your... today is a really bad day for this microphone. Something that you add to your initial expression to remove the divergent terms. So the counter term action is CT stands for counter term. Is simply defined as the minus divergent part of S related. Yes. Yes. But we will, the aim is to, at this level it's still very ad hoc, it's still at the level of kind of removing by hand something. And what we want to show eventually is that this something can be done respecting the symmetry of ADS, which was our guiding principle. And so that will kind of make this prescription a little bit more sensible. So then the regulated action after adding the counter term, then it has the properties that we like, right? So we'll give just a finite result after removing the cutoff. So we define the subtractive action as simply S regulated plus S counter term. So these are these are completely trivial steps which I'm doing, just following the usual exposition, right? So this S subtracted is going to be given only by this part here, where all this part has been removed by the counter term. So this subtractive action is used to compute, for example, the correlation function that you are interested in. And the rule is that you compute whatever you need to compute with this subtractive action. And so first compute, and then send the regulator to 0. So as in any computation, you first compute in the regulated theory, regulated setup, and then send the regulator, remove the cutoff of the regulator at the end. So with this kind of a caveat in mind, then the renormalized action is defined, and at this point it does not depend anymore on phi 0, on epsilon 0, sorry, epsilon that goes to 0, but it still depends on the field, phi 0, for example. Epsilon going to 0 of the subtractive action, which is a function of phi 0 and epsilon. And here where the crucial part comes. Right. So the crucial part is that in order for achieve success, we would like to define the counterterm part in a way that respects the symmetry. So in a way that can be in such that the integrand can be written, for example, respecting the diffeomorphism of ADS and respecting the symmetry of ADS. So it means that we have to rewrite this object that has been defined here in a little bit kind of a naive way in terms of these terms that appear in the expansion after you plug in on shell, etc., etc. You have to be able to write this object here purely in terms of some invariant constructed from the metric, whatever fields we have, right? So, for example, we want to be able to write this contour term here as in terms of some Ricci scalar and other curvature invariants in principle. Right? If you can do that, and this is sufficient to remove all the divergent terms, then it means that this procedure respects the symmetry, and we will see that to a large extent this fixes the ambiguities in which finite terms we can add. So it does not always fix completely, but there is always some explanation of the ambiguity that remains. In particular, in odd dimensions of the boundary, so even dimension in the bulk, there is no ambiguity at all, and all the contour terms are exactly fixed by requiring this symmetry. So there will be a step where we implement this rewriting of the contour term in terms of the original fields, which is the crucial one, and it's also the most tedious one of the recipe. It will involve inverting these expansions, A0, AD, etc., or rather this G0, G1, etc., and rewrite these quantities here in terms, for example, of the metric itself, or the field phi of x of z, etc. And okay, the best way is to understand how this works is to look again at the same example as before, but now with this all of this material in mind. So we will go back to the example of the Klein-Gordon equation. So example. So that's example number one. Example number two will be the metric just in its isolation without any other field. So we will consider later on, at the end of the lecture today, perhaps just the expansion of the metric. For the moment, we consider only the expansion of the field phi. So first example, scalar and fixed metric. ADS. Again, we can be here in general dimension D. So the equation, once again, is this. Now I have one small difference is that I can take general D. So here now I denote this with capital phi for the reason which is clear in a second. So I introduce now a slight change of variable. So my field phi, not capital phi, will be defined up to this term, which I kind of already expect to appear at leading order. Right. So this already looks like some kind of wave function normalization, as we have in field theory, right? So I'm multiplying the original wave function, the original field, by some, I'm extracting some term which will be divergent and putting just in front, right? In any case, at this level, it's just a change of variable. So as I have to solve for the field capital phi, Now I still have to solve for the field small phi. I have already shown two different ways to solve this. So in a way, I mean, it is a little bit boring to have to repeat that. But with this in mind, then let's repeat the computation a little bit. So we insert, and then we expand this. I'm sure that I don't need to have to repeat the steps of the algebra of the simplification of the terms. So let me just give you the result after some slight simplification. We have delta times delta minus d minus m square. So at this point you should probably say that I'm wasting time because we recovered this bit. And then there are some extra bits which look like this, plus z square, d square z phi plus Laplacian in d dimension of phi. Okay, so that's, as I said, it's a third, at least a third way to approach this Klein-Gordon equation. I did the Fourier transform, then I did the bulk to boundary propagator. Now I'm doing this change of variable with this kind of wave function normalization. And but then I recover something which I knew, not surprisingly. So this is 0. Or if I didn't know that it was 0, then this equation forces this to be 0, because I can again expand phi in this kind of a power law expansion, and I would find that at leading order this has to be 0. So let's leave the magic for the moment there. So the ansatz now is, well, and with some experience by now we kind of can guess this. Phi 0 of x plus z square phi 2 of x plus z to the 4 phi 4 of x plus dot dot dot. So here, if you put a linear term, odd powers, in the ansatz and you plug into the equation, they would be set to 0. So here I did answer your question earlier, that here there is no odd power if you put into the equation, they are set to 0. Right, so the term that multiplies this into this expansion will give this bit, and so we are left with a set of recursive equations for the remaining bit. Okay, so what do I want to write? Okay, I don't want to write the expansion with all the terms, right? So you have to take this and plug. So there will be terms coming from here, terms coming from here, coming from there. And then rearrange whatever you obtain, again in powers of z, right? And you have to put to 0 separately each coefficient of the series in z. So at first non-trivial order, the equation looks like this. You get 1 plus d minus 2 delta phi subscript 2 of x plus phi subscript 2 of x plus half box of phi 0 of x equal to 0. So the reason why it's written in this way in my notes, it's because one term comes from from this term, the second term comes from this, and then you have the box part, which is this one. So this is now an algebraic equation. So it's not anymore a differential equation. It's an algebraic equation for phi 2. So once I've solved for phi 0, and in this case there was nothing that fixes phi 0, so phi 0 is my free variable, it's my boundary value. And then, as promised, phi 2 is fixed uniquely in terms of phi 0, and I can just write the solution. So phi 2 is given by minus box of phi 0 divided by 2d plus 2 minus 2 delta. At next order, did I want to leave the metric? Well, okay, I will rewrite the metric when it's needed. At next order, you get a similar equation, and you get that phi 4 is equal to 1 over 4, 2 delta minus d minus 4, box of phi 2. So it's completely straightforward to obtain the equation. It always looks the same with different coefficients, right? And these coefficients somehow change as you go up in order. So they always depend on some delta, on some d, and then some number. This is 4 that depends on which it's correlated with this order here. And in fact, in general, phi order 2n is given by 1 over 2n 2 delta minus d minus 2n phi of the previous one. That's a 2n. Yeah. Now, this procedure, obviously, as you might already be worried, needs to be modified if at some point one of these denominators is 0. Right? I cannot go on indefinitely like that. If at some point, as soon as I increase n, right, n keeps increasing, and if delta was some particular value, namely some integer, then it could be that at some point the denominator vanishes. So this vanishing of the denominator is, in fact, analogous. It's perfectly analogous to the fact that the logarithmic term in the metric appeared at some point. For the same reason, when we are going to expand the equation of motion for the metric, and you plug this expansion, because the metric had, as we observe, has a formally delta equal t dimension, at some point one of the denominators in the recursive expansion becomes 0, and that's why you have to modify the expansion and insert a logarithmic term. And with the logarithmic term, you can still go on and continue solving. And similarly here, so if, so this is a kind of a toy model for the metric itself. If at some point there exists an integer k such that this is 0, then the expansion is modified by inserting a well, I have no space here, so I'll put it here. By inserting a logarithmic term. So if this is true, then phi of x z is equal to phi naught of x dot 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 dots plus z to the 2 delta minus d phi to k of x plus log square, and then there is a new term which is called phi twiddle to k of of x, and then the parenthesis closes and the dots continue. So as for the expansion for the metric, this is has a similar interpretation. It means that when you do this recursive expansion, all the terms up to this term here are determined by this recursive formula. And then when you get to the stage that the denominator would be 0, then you cannot do this. And then you have to change the expansion, so you insert a new term. And then it turns out that you can determine everything up to this level except this term here. This term here remains free. And from now on, everything else is determined in terms of the remaining fields.
The singularities are not a signal of physical singularities in the part.
Which singularities?
When we get the denominator equal to 0.
It's not a singularity, it's just the fact that your ansatz doesn't work.
Okay, so this means that the Pfefferman-Gram expansion could be is valid in the part, right? In all the part. What if there is, let's say, a black hole inside the ATS?
Well, the Pfefferman-Gram expansion will not be able to tell you something about the horizon of the black hole very easily, because it's an expansion near to the boundary. So as much as you push it inside, this is not really information about the far away in the deep infrared. So in fact, to obtain information, I mean, it's the other way around, is the fact that if you have a full solution, maybe even numerical, it doesn't have to be exact solution, but if you have a full solution, then you have to ensure that there is some regularity condition in the interior, a bit like we did yesterday for the Bessel function. Right? That you really need a full solution. You can't just live with the perturbative expansion. And then that full solution, because it fixes an additional condition, it somehow relates to fixing this condition here. Right? So the boundary condition fixes this one, and this that would be free, so it is free from this point of view, but from the point of view of a global solution which is regular everywhere, typically it's fixed by the other conditions, but you really need the full solution to see that. Yeah, and as I said, this is not really a singularity, it's just that there was a naive choice of ansatz. How are we doing with time? Okay, it is possible to have a break. Okay, let's take a break after this question, and a quick one, right? No more than 5 minutes. Okay, there were some questions during the break. Okay, let's just briefly recap. So this is undetermined. By these expansions. And all these terms are determined up to the level, the previous level here. And this phi tilde is also determined. So it takes a slightly different expression from the generic one. Let's write that. So the phi tilde is given by simply minus half of box phi 2k minus 2. Okay. So this one relates to the previous one here, which in turn then goes back, and you can relate this back to phi 0 in the end. So we have now solved for all the terms up to the interesting order, and the subleading terms can all be determined, but in fact they will not play a role in this computation because they are subleading in Z. So when we compute the on-shell action, they will just go to 0 when I take away the regulator. Now let's prepare the action in a way that it's useful to plug this expansion in. So we write once again the action in D plus 1 dimension. Just to say that we are computing exactly the same action that we computed before. Where here in my notation, I guess now this is a capital phi. So we integrate by parts, we pick up the boundary term, and then we insert the expression for the ansatz of capital phi as Z to the D minus delta times the small phi, and then we insert the expansion. So before inserting the expansion, at the stage that I write this in terms of the small phi, this becomes some constant, then an integral in D, x, Z equal epsilon, 1 over epsilon to delta minus D. And then there are two terms from this change of variables. There is a quadratic term, and then there is a term which is phi, that's the usual one, the epsilon phi. Okay, so this term comes just change of variable between capital phi and small phi. Right, so we have to compute the various object. Well, phi is given there, so let's not write it again. So we have to compute, for example, the term from here. That's done simply as follows. You have this starts, so the constant term drops out, and then this starts with 2 epsilon square phi 2 plus 4 epsilon to the 4th phi 4th, and so on, right? Because this is just the homogeneous. It's just homogeneous, so it picks up the various coefficients. And so after you have done that, and you take into account the various orders, you get the following. So you get the first term, delta minus d minus 2 delta. And the leading term becomes a constant in this expression in terms of phi 0 square. Right? So the leading contribution comes only from this part, and this is already subleading. And then at the next order, both terms contribute, and we get 2 d minus delta phi 0 phi 2. No, sorry, let me combine these two terms. So 2d minus 2 delta plus 2 phi 0 phi 2 epsilon square plus dot 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 dots. So as you go up in terms, you get more and more combinations of various order in the expansions. So we don't really want to look into the details of that, but just to see how is the general structure emerging, how the expansion arranges itself. So once we pull out this most divergent term, then we see that the expansion really respects that general form that I gave at the beginning, where delta is exactly the delta dimension of the scalar operator. So this is a constant, then you have epsilon squared terms, and so on. And of course, the lowest term are still divergent, and then we go on up until you will hit eventually a term which is logarithmic, and then after that, all the terms will be finite or going to zero when epsilon goes to zero. So that's okay. We can leave that for the moment. No, I'll leave the So in particular, we have that A0 is equal to minus C L to D minus 1, D minus delta. A2 is equal to this, well, let's say this was A0, then this is A2. Okay, so you can really continue and determine all the terms. Let's write A2 just, for example, in terms of phi 0. So you get C to D minus 1, D minus delta plus 1 divided by D minus 2 delta plus 2, phi 0, box phi 0. Okay, so now, if you follow this this kind of mechanical procedure, then all the terms in the expansion will be determined by phi 0, apart from the logarithmic term, in the case that this was a special dimension delta. Otherwise, everything is really determined. And the next thing that we want to do is to invert the expansion, as I said, and write the various phi 0, well, phi 0 and all the descendants from that, in terms of the original field phi, right? And which will be defined at the arbitrary value z from the boundary. So this is best understood by doing it in practice. Right, so we want to determine phi 0 of x as a function of phi of x in z. Right? So we have to invert that expansion, and obviously you have to do it in a perturbative fashion, so you can again rearrange the expansion in terms of powers of z or powers of epsilon, and you find the following. You find that phi 0 is given by epsilon to the minus d plus delta minus 1 over 2 delta minus d minus 2 delta gamma where gamma is the metric defined as 1 over epsilon square delta ij. So this is really the metric that appears in the ADS metric. So here, remember, we are not expanding the metric, so we don't have G0, G1, etc. We have just the metric which is fixed, right? It's just the ADS metric. And we want to rewrite everything in terms of a metric defined at an arbitrary epsilon. So I really have to insert this 1 over epsilon square that appeared in front of the Minkowski metric. So it's the Minkowski metric plus the conformal factor, well, not plus, times the conformal factor. And then I rewrite the Laplacian in terms of this gamma, that is a gamma that is defined at any value of epsilon. It's not just the leading order term. So this becomes more important when we are considering expansion of the metric, where G0 is different from the term G of epsilon, which is something which involves all the terms in perturbation theory. Okay, so now it's just a tedious exercise. So you have phi naught. Should I also give you phi 2? Let me give you phi 2 as well. Phi 2 is epsilon minus d plus delta minus 2, 1 over 2, 2 delta minus d minus 2, gamma capital phi of x of epsilon. So I inverted this up to order epsilon square. Right? If I want to go in higher orders, so what I'm doing here is, strictly speaking, valid only for k quite small. If I want to obtain a result for higher orders with a higher k, then I'd have to go up in higher order here, and I have to include more terms. Okay, so this is a check I don't want to do. So at this stage, it only remains to plug into the action. So the counterterm action then becomes now, importantly, a function of capital phi. So you see there, you are here. You have phi 0 square and phi 0, phi 2. And for phi 2, you substitute phi 0. So you get this expression. And then into that, you plug this phi 0. And then you expand again. And the result is the following. So it's crucial to track the notation. So this is the capital phi. That's the field that lives in the bulk. Square. And the next order you get after things simplify and rearrange a bit. So you have to do a little bit of algebra. Capital phi. Laplacian capital phi. Okay. So, as I said, there are also higher order terms, but for just for illustrative purposes, I just want to focus on the first terms, which are the most universal ones, because they arise, especially the first one, arises always. So, in fact, these counterterms here, they are sufficient to renormalize operators of dimension delta less than d over 2 plus 2. So for illustrative purposes, I consider these low values of delta. If we had more time and more patience and larger boards, we could go up in order and then obtain more counter terms. And all will have to be written in terms of capital phi and this gamma there and various derivatives. So you get higher derivative terms as you go up in the expansion. I don't think there should be any epsilon at this stage, no. So I forgot an important, actually I mixed up two notations, sorry. So that's why you probably got confused, because I simplified my terms in the notes and I removed the epsilon. So conceptually this is an important point, because you want to be able to write the expression here independent of any epsilon. So of course there are factors of epsilon inside, that's secret, right? In the sense that you have written the determinant, I mean what was here written as epsilon to some d minus d, it's written as a determinant of the metric. And then the various terms that appear here explicitly in epsilon, these, and all this one that I have not written, now are secretly contained into this capital phi, gamma, etc. But the point is that once you have reformulated this in this way, this is now something which has the full symmetry of the bulk. It's written in an equivariant way. So then this is a good counter term according to my initial prescription. So it's not something that it's not anymore as ad hoc as it appeared at the beginning, where you just take whatever multiplied epsilon with the epsilon itself and just subtract it. Now I have shown that such terms, which are the divergent terms, can actually be rewritten in this way. And the other comment is that going back to the logarithmic term, which kind of plays a special role in the discussion, the term that in this expansion here, you see here there is 2 delta minus d minus 2, and then as you go up, these denominators will keep having a different number here, and then at some point you would hit the point where the denominator comes from the one that was 0 in my particular case. So, for example, to be concrete, if delta is equal to 2 over 2, d over 2 plus 1, right, then already this term would be 0 in the denominator. So I have already seemingly a problem. As I said, it's not really a problem, it's that you have to modify the expansion, and the logarithm really appears early on. At the second stage of the expansion, there is already the logarithm, and that means that you have to substitute this term. But it's not really a substitution by hand, it's just that you're using a slightly different expansion. And the net result is that it looks like you're substituting this with a minus half. I'm not really 100% sure about the factor, but anyway, I'm writing what I have. So the coefficient of this same term, instead of becoming this, has to be written as a logarithm. So this is the only term which evades this this prescription of having to be written independently of epsilon. So there is no way I can reabsorb this log epsilon in this case. And actually this has a physical interpretation, and interpretation is something which I would like to discuss in the next half an hour, or at least start that discussion and go as far as possible. And it has to do with the appearance of anomalies. In particular, the Weil anomaly, the anomaly on the trace of the energy momentum tensor, receives various contribution, and it receives contribution exactly from these logarithmic terms. So this term here would contribute to the anomaly in that case.
So can you just run over the argument again as to why hiding the epsilons and the gamma makes it covariant? I don't really see how this is any better. Because all we've done is put them somewhere else. It's still there. It's still epsilon.
I'm not really understanding your comment. Of course, it's equivalent, but you know, if something was not manifestly symmetric and you write it in a manifest symmetric way, then you have shown that it is symmetric, right? If I say that, I don't know, let me just write something stupid. E1, B1 plus E2, B2, I don't know, you don't see that it's invariant under rotations unless then you don't rewrite these as E vector B. I made the symmetry manifest, so this is invariant. I mean, it's manifestly diffeomorphic invariant. It's written in terms of the metric, and well, here you don't have curvature invariance because the metric itself doesn't play a dynamical role, but you have the Laplacian computed with the metric gamma, the determinant of gamma, and then the poor scalar, what can it do? I mean, just the scalar. So it's just written as the bulk scalar. If it was a field with indices, it would be contracted in the appropriate way. So by rewriting, I mean, the lesson is that by rewriting something in a different way, you can highlight some symmetries. And in fact, you fail to highlight that symmetry for this logarithmic term. And that has a consequence, which I would like to explore in the next half an hour. Okay, as you can guess from these expansions here, I mean, I presented kind of the minimal and the simplest possible terms, but they become a little bit cumbersome to work out at subsequent orders. I can give you the references if you want to see more details about this. Okay, so in this last half an hour, I would like to discuss the so-called holographic Weyl anomaly, which is perhaps the most spectacular outcome of this holographic normalization. In fact, historically, Henningsen and Skandari's paper derived the holographic Weyl anomaly before the holographic normalization was formulated in a systematic way. And it was like precursor to that. So the technique that was explored in the Weyl anomaly paper was then generalized to become the holographic normalization method. So I'm presenting the things in inverse historical order. So I will now go back to the metric, to considering the metric alone, in isolation, although then one can combine, as I said, the metric with other fields, and then essentially one could obtain various contributions, for example, to the anomaly, coming from the metric and coming from the scalars and coming from whatever other matter fields that you have. So, okay, I already presented the Pfefferman-Graham expansion. So all I have to say is that this procedure here, which I have described for the scalar, can be carried out also for the metric in the Pfefferman-Graham coordinates. Right? So focus on metric. Use the Pfefferman-Graham expansion. Which means determine the various expansion coefficients g, let's say 2n of x ij in recursive fashion, and then plug into the action, rearrange the action on shell in terms of some power expansion in epsilon up to some logarithmic term. And then the final and most painful step, invert the expansion and rewrite that, which was written in terms of G0, in terms of the big G, the G that lives in the bulk. That's quite tedious, so we will not do all of that. But again, I will highlight some steps, and then I will focus on the logarithmic term and explain how that gives rise to the anomaly. Or in the process, I will also define for you what anomaly I'm talking about and what is the general expectation in the conformal field theory. Now, okay, let's start from the action. So this action is almost something that we have seen already many times, up to one important modification. So it is the usual, I also start putting factor of G Newton. Usual Einstein-Hilbert in ADS action. Now my small d is capital D minus 1 in previous notation. And then there is also a boundary term that one has to add from the beginning, which is the so-called Gibbons-Hawking boundary term. So let's write this and then define what this means. Okay, this is called Gibbons-Hawking term. So gamma is the induced metric on the boundary. So this was studied much before the ADS-CFT correspondence as a term which has to be put whenever the space has a boundary. So it really is more general than ADS. I will make a comment in a second. And this K is a scalar, and it's the trace with the metric gamma. So let's say gamma mu nu, let's call it, of this, which is called the extrinsic curvature. And n mu is the outward pointing normalized normal to the boundary in general. So this term was proposed by Gibbons and Hawking as necessary to have a well-defined variational principle if you study the problem for finding a metric with given boundary conditions. In particular, it becomes important if you want to study the Hamiltonian, for example. And so, as such, it's just a universal term that you always have to consider whenever your space has a boundary, which includes ADS, even though it has a conformal boundary. And in particular, when we think about ADS as this cutoff version, where you put some epsilon different from 0, then it really has a boundary, and then this term is really necessary from the point of view of the variational principle of the classical action. However, as we are doing, actually not however, but in addition, as we are doing the ADS-CFT correspondence, as we've seen, the on-shell action plays a very important role, and the value of the on-shell action really changes completely what we are computing in the field theory side. So unless this term is 0, which has no reason to be in 0 in our cases, then this term is really changing the result that we want to compute from the beginning, right? Unless, again, there are some particular cancellations. But as it turns out, anticipating the result, this term is not 0. It is very important, and if you don't include it, you will not get consistent result. So holographic normalization and holography in general reinforces the fact that you need to add this term in the action. So in this business of making expansions, in particular, then once we reduce this term as a kind of boundary term, then we'll be on the same level of this. So everything will be reduced to some computation on the boundary. And as these terms contain divergent and finite terms, this term also contains divergent and finite terms. So it contributes both to the divergences, and it could contribute actually with a minus sign to that by cancelling some divergences. And it also has a contribution which is finite, and so it is important. However, by itself, this is not sufficient to cancel the divergences. So we should not be led to hope that maybe this term will be acting as a counter term. So this by itself is not a counter term, has to be included, but we still need to do the procedure and find out what are the counter terms to be added. So in general, the on-shell action that you would compute for a gravitational theory would be a bulk action, a boundary term, which is, in this case, the gravitational one. There could be other boundary terms which are necessary for similar reasons, plus the counter terms, which are something which are intrinsically holographic. Yeah.
The divergences of the Gibbons term, to what are related? Because the action, the divergences were related to the volume of ADS, but if you're at the boundary...
Well, you will get, when you plug in simply, you will get terms which go with negative power of epsilon. So in a sense, this is already at infinity. So this is a kind of by itself infinity when you are at the boundary. It is again related to the fact that it is ADS. It's just that now, I mean, if epsilon is finite, this is not divergent and this is not divergent. But as epsilon goes to 0, this is divergent and this is also divergent. Although there is no integration in dz, but there are things which depend on 1 over z, and they diverge.
Why has it been consistent for us not to include this term until now?
Sorry, so repeat the question.
Why has it been okay for us not to include this term until now?
Has been okay. It's a boundary term, so it does not change the equation of motion. Right, so since I was explaining, I was discussing equations of motion and supersymmetry equations. This does not affect any of that discussion. As a boundary term, normally you would be like to neglect it, but as you start deriving the equations of motion, you will see that to have for that procedure to make sense with some particular boundary conditions, then you will find that this term is necessary. So from the classical point of view of the equations of motion, is something which makes well-defined the variational principle. And then you can completely forget and live your life without it. On the other hand, in holography, it becomes immediately crucial because you have to evaluate things on shell. So you cannot do this thing that you have done so far of ignoring its presence. This actually, let me mention this point. This is actually, to some extent, an open problem. Well, to some extent, it has been solved, but it's still not completely solved, to understand how to supersymmetrize these boundary terms. So this is something which is not very intensively studied. There are few papers that have addressed the issue of how to symmetrize these or other boundary terms. And it's an important open point. In particular, it is very important how to understand how to supersymmetrize the counter terms. But this is still up to debate, so it's not for the lectures. Okay, so these were the comments about the Gibbons-Hawking term. And then we go back to our metric, which we write in the Pfeffer-Mann-Grahan expansion. And so let's rewrite it. So now we are in the realm of asymptotically locally ADS spaces, right? Because there is a non-trivial expansion. This is not just the Minkowski metric. And okay, so we have G is equal to G0 plus Z square G2 plus dot dots. G0 is free. G2 is determined recursively. So I gave you the expression for phi 2 in terms of phi 0. Let's do the same for G. So this has to be a tensor. Let's put the indices. So G2 ij in terms of G0 is given by the Riemann tensor, sorry, the Ricci tensor constructed out of G0. And this. And the Ricci scalar. Okay, so this is the Riemann, sorry again, the Ricci tensor constructed out of the metric G0. And this is the Ricci scalar. Okay, so altogether this is a tensor, which is what G2 is. So this fits on a line, it's kind of cute. G4 would be already tedious and cumbersome, so I'm not going to start writing higher order terms. In fact, for many practical purposes, especially in D equal 4, I mean, G2 is all you need really to get you going. Okay. So as for the scalar, all the terms are determined up to G D minus 2 ij. And then GD plays the role of the term which had a logarithmic bit. But for this term which is determined, which is undetermined, so this term which is undetermined, we know that some properties of it are fixed. So because it's a tensor, for example, we can compute. So let's say if we are in D equal 4, and the trace of G4, that would be GD in general. But for this one is given by 1/4 trace of G2 square. And yeah, also its covariant derivative is fixed. Right, so here traces are taken with G0. So there is this notation in which you regard G4, GD, etc. as matrices, and then you multiply them as matrices, and you raise the indices always with the inverse of G0. In that sense, these traces are defined. Okay, so the action, if you carry this out, and then you take, you plug this into the on-shell action, and plugging into the on-shell action means plugging into this term, and as I already showed you at the beginning, this term just reduces to a constant, a different constant on shell. So that's kind of analogous to the trick of doing the integration by parts for the scalar. So this is not quite a boundary term, but once you write this as a constant, then it quickly becomes like a boundary term because it really has some integral up to some coordinate z, and then it's a simple power law power law terms, then you can integrate term by term and get in some contribution, which is then on the same footing as that. Then you have to do this inversion procedure, when you have to rewrite everything in terms not of G0, but in terms of G, the G that appears there, Gij. So that's a little bit tedious, but the final result is the following. The counter term action defined again at some z equal to epsilon so has a constant which is kind of analogous to the constant term with phi 0 square that appeared for the scalar. Then it has a rich scalar so this is computed with Gij. Right? So in particular, this R, it is not the R naught that appears there. So this R naught is computed with G0, the leading order term in the expansion. This R is computed with G, the full G. So then you have to, again, expand this, and as was a complaint earlier, this again becomes terms in epsilon, and of course, once you have expanded this in epsilon, then it will match to the expansion in epsilon that it's where you started from. But you have rewritten everything in terms of things which are manifestly diffeomorphic invariant in terms of your fields, not about the coefficient in the expansion. Let's also write the next term. The next term is L cubed divided by 2d minus 4 divided by 2d minus 2 square. And then you have this combination, which we will keep discussing for a bit, also tomorrow. So you have the square of the Ricci tensor, contraction of the Ricci tensor, d times d minus 1 r square. And that's the square of the Ricci scalar. And, okay, and then plus dot dot dots. Right? So how do I read this counter term action? Well, I have to read it as follows. This term is always present in any dimension. The expansion has to be modified as soon as I find some denominator that vanishes. So for example, in 2 dimension, this term, it doesn't make sense, and then you have to substitute this with the logarithmic term. If you are in 4 dimension, then you have this term with d minus 2 equal to 2, right? So you just write it, and then you keep going, and you find the next term is divided by d minus 4, so this doesn't make sense, and you have to substitute this term with the logarithmic term times the same invariant. I called it gamma in the scalar discussion, and also there, you're right. But
Also R maybe is K.
R is K. What?
It's also induced, right?
Sorry, I didn't get this.
Some kind of induced curvature or not.
No, this is not an extrinsic curvature. This is just some intrinsic curvature of the boundary metric. That's the usual curvature, usual Riemannian curvature. But it's computed with G, this G here. And I agree that in that part of the board, this was called gamma. So that's the only modification that I have to do to match these 2 sides of the board. Yeah, so this G here is a G in d plus 1, Okay? Hopefully, I know that this was a bit confusing, but hopefully you can trace. So this is gamma. So for example, if we are in d equal 4, then instead of this term here, you will get the term minus L cube divided by 2 d minus 2 square. So it is literally the d minus 4 bit, or here the d minus 2 bit, that it has to be removed as a practical rule. It's the outcome of the computation in the modified ansatz with the logarithmic term. So you remove that meaningless term, and you replace that with log epsilon, and you keep the rest. Right, so here you have 1 over 4 times 3 r squared. So this term is what replaces this term, which in practice is just replace the d minus 4 with log epsilon. Okay, so we are almost out of time. What do I want to say before we have the break? Okay, I want to say what are we going to do with this term tomorrow. So with this term, we are going to reproduce the original derivation of Henningson and Scandaris of the holographic Weyl anomaly. So maybe I should tell you what is the Weyl anomaly in general. Right? So in a conformal field theory, because of invariance under dilatation, one of the word identities of the conformal field theory is that the expectation value, so here we are back in the quantum realm, of the trace of the energy momentum tensor, that would be 0, but it's not quite 0 because there is an anomaly. Right? So as you have seen in the extensive lecture course of Bilal, an anomaly in a quantum field theory is the breaking of the symmetry by some quantum effect. So here the symmetry is the symmetry under rescaling, under conformal rescaling, and that's broken by quantum effects, and it leads to a non-vanishing trace of the energy momentum tensor. So I stress that it's a quantum effect that if you consider just a classical theory which is invariant under the conformal group, and you compute its energy momentum tensor, you would find automatically that it's 0, the trace. So you need to do some quantum computation in order to find out that it is different from 0 and it's equal to some expression. And what is this expression? Then, well, it depends the way in which you view the anomaly. For example, if you view the anomaly as arising in some background field, you probably have seen the background gauge field discussion where you had the F tilde term that appear in the non-conservation of the chiral of the current. And similarly here, in this non-conservation here, the Weyl anomaly, the conformal anomaly, will be expressed in terms of some background, but the background here in general will contain the metric itself. So we have to think to be in some non-trivial background. And it may also contain additional terms if you have additional bulk fields, but I will concentrate on the contribution from the metric alone. So I think it is now time to stop. And tomorrow we will resume by showing how this term then directly propagates to this A. And we'll then explain that whatever is the result matches exactly with what is the expectation in the field theory side.